Hello students, welcome to this module 2 of the course CHE 614 on Introduction to Hydrodynamic Stability. So we'll continue with the introduction and motivation of the subject that we started off in the first lecture. Now in the first lecture I focused on laminar turbulent transition in a pipe, and I told you how fluid flow undergoes a rather dramatic transition from a very smooth orderly flow state, which we call laminar, to a very complicated and disorderly unsteady flow, which we call turbulent. And we mentioned that the subject of hydrodynamic stability concerns itself with how understanding or explaining how this transition happens from the laminar to turbulent flows. Now this is not the only goal of the subject of hydrodynamic stability. Now there are other geometries, for example flow between two concentric cylinders. Let me draw this schematically here. Suppose you rotate the inner cylinder and fluid is in the gap. Okay, now if you look at the top view of this geometry, let me draw a circle properly. Okay, okay, now this is I'm sorry about this. Okay, this region is solid, it's not available for flow. Fluid is present in the gap between the two concentric cylinders, and one of the simplest solutions that you might have derived, we know that the inner cylinder is moving with an angular velocity omega. In a cylindrical coordinate system, one of the simplest solutions, which is one of the laminar solutions that we can derive analytically from Navier-Stokes equations, is that you have v theta, which is the azimuthal velocity in the cylindrical coordinate system, non-zero, and then you have Vr is 0, the radial velocity, and the axial velocity all being 0, and this is a steady function, that is, it's independent of time. Okay, this geometry and the associated flow is called the Taylor-Couette flow. Okay, this is different from the plane Couette flow, which is the flow that is generated when there is relative motion between two parallel plates. The Taylor-Couette flow is the circular or cylindrical version of it, but one might imagine that in the limit when the gap thickness becomes very small compared to the either the inner or outer radius of the cylinders, then one might locally, then the annulus will be so gently curved that locally, let's say one of the boundaries is moving, then you will get the plane Couette profile locally, although the curvature is there, but it is so gentle that you will not be able to see it. Now this is another example of a laminar flow. Now what the English scientist, the British scientist J.I. Taylor observed in the early 1920s or early 1930s was that if the angular velocity of the inner cylinder keeps increasing, the outer cylinder is stationary, let's assume, then beyond a critical angular velocity, what happens is that the azimuthal nature of the flow is now destroyed. Then you will start seeing rolls. Okay, these are rolls. Okay, these rolls are going around the, so there is a flow, it is driven by the angular velocity of the inner cylinder. Okay, the inner cylinder is solid. Now this is going around. I'm just drawing a cut cross section of the same, right? So this is going around and like this. Okay, so these are, so this basic flow, which was purely azimuthal, now gives rise to or transitions to a more complicated flow. These are not turbulent. This flow is not turbulent, whatever that that follows the transition. Okay, there is a laminar unidirectional flow in the azimuthal direction to a time periodic flow. Okay, but it is still not very complex. It's not turbulent, but it is certainly more complex compared to the basic laminar flow. Okay, this happens when the so-called Taylor number exceeds a critical value. Okay, so this is denoted as Taylor number is denoted as TA. Okay, these are called Taylor rolls or Taylor cells. And the basic physical idea here is that the driving force that drives a fluid from this state to this state is centrifugal effects, centrifugal force, which tend to throw the fluid because there is a rotating, the inner cylinder is rotating, then there is a centrifugal force acting from inside to outside, and that pushes the fluid beyond a critical angular velocity. But then the fluid cannot go indefinitely because there is an outer wall, so it has to come back. So this forms the roll. Okay, the other instability is called the thermal convection or the Rayleigh-Benard instability. Here what one has is very simple. You have two parallel plates. Let's say you fill some viscous liquid like an oil, and the bottom temperature is T1, the top temperature is T2, and T1 is greater than T2. Okay, so there is a temperature gradient in this direction. T1 is high, T2 is low. It's a linear temperature profile. This is the conduction state. If you solve for the heat conduction equation between these two plates, assuming no fluid motion or convection, the pure conduction state will result in a linear temperature difference, linearly varying temperature profile. And but this is inherently unstable for the following reason. This is potentially unstable for the following reason, that if I take a small parcel of fluid that is close to the bottom, now here the temperature is more compared to what is near the top, so that means that the density of this small parcel, okay, of fluid is lighter, okay, compared to the density. The fluid in this small pocket is lighter compared to the fluid here, so this will tend to move up due to buoyancy, and it will occupy this place here, and whatever that was there will come down. Okay, this is also going to result in rolls which are called convection rolls. Thermal convection rolls or convection rolls. This is an example of natural convection. So again, the fluid will start going in rolls like this. This is these are two parallel plates. Okay, and you know that density of a fluid decreases with increase in temperature. Okay, that's what results in a net buoyancy force that pushes the fluid up and the heavy fluid comes down. Now this is something that you can observe even in a domestic setting, wherein if you take a pan and then you coat the pan with a layer of oil, and then you start heating it in a stove, and then if you sprinkle some powder like pepper powder or something for aiding in visualization, then what you will be able to see is some nice pattern from, if you look at it from the top, and that will be basically the convection rolls. And this is slightly different from this problem. Here both the fluid is bounded by rigid walls on both sides, whereas here the bottom is the pan, whereas the top is of course the bottom is where you are heating, and then you put a thin layer of oil, let's say, and then you start heating, and then you put some, sprinkle some pepper powder, you'll see nice patterns upon heating. That is also an example of convection rules. Okay, so here also there is an instability, we say, that takes the flow from this conduction base state to this state. This is the state of convection rules. Okay, now the subject of hydrodynamic stability is also concerned with understanding not just laminar to turbulent flows, but how a simple flow breaks down to a more complex flow like this in these two examples. I also mentioned the other example wherein you have a cylindrical jet of liquid, and that eventually becomes unstable and then starts to break up into drops. Okay, all these are examples of how the system or a fluid mechanical system transitions from one state, a simpler state, to a more complex state. And in one of the most important examples, that complex state is fully turbulent state, okay, as in the case of pipe flow experiment. Now, why do we study hydrodynamic stability? Relevance to engineering. We study hydrodynamic stability because in laminar flow you have low drag compared to turbulent flow. That is, if I fix the Reynolds number and then look at the friction factor versus Reynolds chart for pipe flow, I told you that this is laminar, this is turbulent. For a fixed Reynolds number, the turbulent line will have a higher drag than the laminar line. Okay, so obviously from the point of view of pumping costs, you would prefer lower drag, that is laminar flow is preferred. But you also should note that laminar flow is marked by the presence of usually in rectilinear flows parallel streamlines. Even otherwise the streamlines aren't too complicated. Suppose I take a parcel of some you put a parcel of a die, then this die will be convected in this direction, in the flow direction, but in the other direction it cannot be convected because the flow is purely parallel, so it has to only diffuse. So in pure laminar flows with very simple streamlines, the cross streamline transport of heat or mass is limited only by diffusion. Diffusion is the only mode of diffusion or conduction. Okay, conduction or diffusion of transport in directions perpendicular to the flow. Okay, now on the other hand, if you look at turbulent flow, what I told you in the last lecture is that even though in a turbulent flow between, let's say, in a pipe due to a pressure gradient across the pipe, even though the pressure gradient is acting only to push the flow in this direction, but the details of the flow, so the flow is on the average moving in this direction, but if you look at small scales in the flow, there is very complicated motion in all three dimensions. So these are called turbulent eddies. Okay, so these turbulent eddies will help in transporting. Suppose I put a piece of die, okay, as in Reynolds' experiments, these will be very vigorously transported to various parts of the flow due to these fluctuating turbulent eddies, and therefore turbulent flows are characterized by very good mixing. So this is the advantage. In contrast, laminar flows are characterized by poor mixing or no mixing. Okay, but on the other hand, turbulent flows have very high drag. Okay, so the idea of understanding understanding hydrodynamic instability is better will throw some light on how to reduce these pumping costs in a turbulent flow. Right? Is there a way to postpone the transition? Is there a way to control the transition? These are the practical motivations for understanding the laminar turbulent transition in great detail. Okay. Now, how do we study this subject. What are the methods or tools that are used in the field of hydrodynamic stability? First and foremost is experimental observations. These are, as in any field of science, experimental observations are extremely crucial. There are two types though. One are naturally occurring phenomena, and then other are laboratory experiments. Okay, you can use both to improve our understanding of hydrodynamic instabilities. The other is a truly computational approach. These are called direct numerical simulations, or DNS. And third is to understand instabilities via mathematical analysis. And the focus of this course is in this approach. This is not to say that the other two approaches are not important, but of course they have their own strengths. But one of the main ideas that has emerged in the last 100 years or so of research or so in this field is that the mathematical analysis of instabilities can provide a very significant insight into how fluids flows become unstable, which will also help us in the computational understanding of such instabilities, and also in carrying out experiments under the right parameter regimes. So this is the goal of this course, namely a mathematical understanding of or prediction of hydrodynamic instabilities, such as the ones that I've just mentioned, pipe Poiseuille flow or plane Poiseuille flow, or the Rayleigh-Benard thermal convection, and so on. Okay. Now, before I sort of go into the details of the subject, I want to get all of us on the same page by discussing some preliminaries. In this course, I'm going to restrict myself to Newtonian fluids. Newtonian fluids are fluids that obey the Newtonian constitutive relation, which states that the shear stress is directly proportional to del V, the symmetric part of the velocity gradient, and the constant of proportionality is called the shear viscosity, or simply the viscosity of the fluid. Now, the symbols for viscosity are typically mu and eta, and I might switch between these two as we go along. Okay, the governing equations of motion for Newtonian fluids are called the Navier-Stokes equations. Okay, these are the continuity del dot V equal to 0. This is the mass conservation or continuity equation for an incompressible flow. I'm going to assume, okay, and then we also have the momentum equation, minus del P plus mu del squared V plus body force rho G. The left side of this is the mass times unit volume, which is rho, times the rate of change of velocity as you follow a material particle, that is, as you follow a fixed set of fluid points. It's not if you take simply the time derivative at a given location, then that is a partial derivative of that variable like velocity with time. But here we are adding the convected component, that is, a fluid particle is not just staying put and it is moving, and you are trying to measure the rate of change of any property like the velocity following the particle. That is called that is this entire derivative, and this is called the substantial derivative or material derivative in different fields of mechanics. Okay, the left side is simply mass per acceleration, mass times acceleration per unit volume, and the right side has sum of all the forces acting on a fluid element. These are the pressure gradient forces or pressure forces. These are the viscous forces due to fluid viscosity, and these are the body forces due to gravity. There can be other body forces also if you have electric fields or magnetic fields and so on, but we will not include them here. Okay, and of course you will need the governing equations plus boundary conditions. Typically these are the no slip boundary conditions. I will if you have rigid channels, I will discuss a little bit about boundary conditions for two fluids flowing adjacent to each other a little bit later, but right now let's assume that you have well defined boundary conditions such as the no slip conditions. Alright, so this Navier-Stokes equations are believed to be perfect in the sense that they describe all the flow states of Newtonian fluids. Okay, so it is not that Navier-Stokes equations can describe only laminar flow. They contain all the information to describe or predict flow fields. The only thing is you should be able to solve them. Now one of the main issues in solving the Navier-Stokes equation is that I'm sorry about this. One of the main issues in solving obtaining mathematical solutions of the Navier-Stokes equations is the presence of this term. This term is non-linear in velocities, and it contains products of velocities and the derivatives, right? So it's non-linear. So this term is one of the most important term in generating turbulent flows in fluids. Okay, so the Navier-Stokes equations are fundamental to understanding the flow of Newtonian fluids. Now, what is the issue with Navier-Stokes equations? Okay, now I want to just compare this set of equations with the equations of heat conduction, unsteady heat conduction. Suppose you have rho Cp partial T by partial T is equal to thermal conductivity times del square T. This is the unsteady heat conduction equation that you would have seen in courses on heat transfer and transport phenomena. So this has a lot of similarities. If you ignore the nonlinear term in V, the convected acceleration term in the Navier-Stokes equations for the moment, and if you say that there are no body forces, and if you ignore the pressure forces for the moment, the equation for velocity is identical to the heat conduction equation. Okay, now the heat conduction equation is a linear equation, assuming K to be constant and rho to be constant, right? Rho, Cp and K to be just constants for of the material. Then this is a linear equation. Whereas a Navier-Stokes equation, in the presence of the convected acceleration term, is a nonlinear equation. Okay. Now there is a lot of difference between linear and nonlinear equations, because in linear equations, if you find a solution to the linear equation that is consistent with the boundary condition, then this solution is unique. Okay, so in other words, if you find a solution of the Navier-Stokes equation, it is the solution. There are no other solutions that are consistent with I'm sorry, not Navier-Stokes equations, the heat equation, the conduction equation. But you cannot say the same thing, and this happens because in linear equations you can show that if a solution is there, it is unique. So this is called uniqueness of solutions. On the other hand, if you do the same for Navier-Stokes equations, if you find a solution to the Navier-Stokes equation, it doesn't automatically guarantee that there are no other solutions. That's because The Navier-Stokes equations are nonlinear in V. So it is the nonlinearity that is fundamentally important, is essential. It's in some form, it is essential for instabilities and onset of transition. Okay, so if you look at a heat conduction equation, if you look at only conduction, then there is nothing like turbulence in this for heat conduction. Why? Because the equations are linear and the solution that you obtain will be always unique. Right. Now, having said this, then we may want to understand how we solved problems of the Navier-Stokes equation in our earlier courses. Okay, I will illustrate this by deriving the solution, the laminar flow solution for pipe Poiseuille flow. Or the Hagen-Poiseuille flow. So what you have is you have a pipe of some radius or diameter, okay, and fluid is flowing due to an applied pressure drop, okay, and we can put coordinate system Z along the axis, R in the radial direction, okay, and theta is going around in the pipe. Now we want to know that if I have a steady pressure drop or pressure difference across the pipe, what is the velocity profile that gets developed in the pipe. You might have of course seen this in the earlier classes, but I want to just do it once so that you understand the assumptions involved while deriving the laminar flow solution. Now if you look at the appendices of many textbooks on fluid mechanics, you will find the equations of continuity and momentum in various coordinate systems. Here we have to use the cylindrical coordinate system. Okay, now we have the continuity equation. Del dot V is 0. Note that del dot V is 0 is partial Vx by partial x plus partial Vy by partial y plus partial Vz by partial z equal to 0 only in a Cartesian system, Cartesian coordinate frame. If you take cylindrical, the same del dot V equal to 0 takes a different form. It takes the form 1 over r partial r Vr plus partial Vz partial z. This is the continuity equation. Now we are going to postulate for the laminar flow that the only non-zero velocity is v, because the forcing is in the z direction, right, and therefore you would expect the flow to be only in the z direction, right, and this is just an assumption. Of course this has to be verified, but this is indeed valid for any Reynolds number or such thing. Okay, so and Vz has to vary in the r direction, Vz of r, right, and it's independent of z. This is called the fully developed flow assumption. The flow velocity is independent of the flow direction itself. This is called fully developed flow. And the next thing is we're going to assume that, so if you do this assumption, then partial Vz by partial z becomes 0. The next thing we are going to assume is that things are independent of theta. The flow is axisymmetric. Okay, this is called the axisymmetric assumption. That is partial theta of any quantity is 0. This is called the fully developed assumption. Okay, now this leaves us with a very simple equation from the continuity equation, which is 1 over r partial r of RVR is 0. If I integrate this one, partial r of RVR is equal to some constant C1 R okay. So let's just do this a little bit clearly. This means that partial of RVR is 0. 1 over R cannot be 0. So that means that partial R of RVR is 0. If I integrate this once, I'll get RVR is equal to some constant C1. Okay. Now VR is 0 at R is equal to 1 at the rigid wall. So if I put R is equal to 1, I'll get VR is equal to C1 is equal to 0 or C1 is 0. Okay. So that means that VR, if at the boundary you have 0 velocity, then it is the same everywhere. This comes directly from the continuity equation. Okay. Now the next thing is, so we have V theta is 0. This is axisymmetric flow, and Vz is a function only of Vz is independent of z, it's independent of theta, so Vz is a function only of R. Okay. Now let's look at, this is all the continuity equation will tell us that Vr is 0. Let's look at the z momentum equation. There are 3 momentum equations. Momentum is a vector. You have the z momentum equation, the R momentum equation, and the theta momentum equation. But the most important momentum equation is z, because the main driving force is in the z direction. So let's write down the momentum equation. Partial Vz partial t plus Vz partial Vz by partial z plus V R partial Vz by partial R plus 1 over R V theta partial Vz by partial theta is equal to dP dz, the pressure gradient, plus mu times 1 over R partial R of R Vz dr plus partial squared Vz z squared plus 1 over R squared partial squared Vz partial theta squared. Now let's drop all these terms which are 0 due to the assumptions. Now the flow is steady, so this is 0. The flow is fully developed, so Vz is independent of z. Alright, now we found out from the continuity equation that Vr is 0, and here Vz is independent of theta, it's axisymmetric flow. So all the terms on the left side becomes 0. Alright, so now on the right side you have this is 0 because of fully developed flow, and this is 0 because of axisymmetry. So all you have is just this term. Now we can call minus dP dz as P1 minus P2 by L delta L, and L. Okay, and this is the pressure at the pressure at the entry. This is the pressure at the exit. This is the pressure difference or pressure drop. Okay, so what you will find is, therefore, and we'll call delta P as P1 minus P2. So minus partial P partial Z is delta V by L. Okay. Now, if I rewrite this, mu 1 by R partial R of R partial Vz by partial R, okay, is equal to minus delta P by L. Okay, if I bring this mu to this side, to the denominator, Okay, now this is the equation that you want to solve for Vz, the flow direction velocity. Okay, so if I integrate this once, I will get, sorry, if I integrate this once, I'll get so I have to take this r to the other side as well. So if I integrate this once, I'll get r partial Vz by partial r is minus delta p by 2 mu L r squared. Okay, right? Sorry, let me write it properly. R squared plus you'll pick up a constant, right? Now let me copy this. Here. Okay, now I can bring this r here. Okay, this will become C1 by r, and I will also get rid of an r because I have cancelled. So this is partial Vz partial r. Okay, and okay, now if I integrate this once more, right, I'll get Vz is minus delta p by 4 mu L r squared plus, this is mu, okay, plus C1 ln r plus C2. Okay, now at r equal to 0, the center of the axis of the cylindrical pipe, Vz cannot diverge. Vz is finite. Okay, that means that the coefficients multiplying ln r, this must be 0, because ln r goes to diverges as r goes to 0, so you cannot have diverging velocities as r goes to 0. So you will find that the constant C1 has to become 0. Therefore you are left with Vz is minus delta p by L, this is the pressure gradient, 1 over mu r squared by 4 plus C2. Now we need one more one boundary condition to fix this constant C2, but we know that at r is equal to capital R, Vz is 0, the no slip boundary condition. Alright, so now this becomes, if I integrate this once, if I substitute small r is equal to capital R and substitute 0 for Vz, so I'll get C2 is delta p by L 1 over 4 mu r squared. Okay, therefore Vz of r after fixing the boundary conditions is delta p by L 1 over 4 mu r squared minus r squared. This is the radius of the pipe, and this is the radial coordinate of the cylindrical coordinate system. Okay, all right, now this can be written slightly differently by cleaning up delta p by L r squared. I'm pulling out an r squared, so I'll get 1 minus r by r whole squared. Okay, so if this is the velocity profile, then one can find Q, the volumetric flow rate. Okay, as you have to integrate 2 pi 0 to r Vz r dr. Okay, now you have to simply substitute this out here, out here, and then do the integration. It's a straightforward integration. So you'll find that this is nothing but Q is equal to delta p pi d to the 4 by 128 mu L, where d is the diameter of the pipe, which is twice the radius of the pipe. Okay, so this is the relation between pressure difference delta p or pressure drop delta P by L as a function of this is the volumetric flow rate as a function of pressure difference, diameter, and it's inversely proportional to the viscosity and so on. Okay, this is what eventually leads to if I define suitably if I define V as Q by pi r squared, okay, and then define the appropriate friction factor, then I will get F goes as 1 over Re, the constant being really defined by how you define F. Okay, so this is the laminar velocity profile, which is the famous parabolic velocity profile. Okay, this is the parabolic velocity profile for flow in a pipe. Okay, now this is what leads to the friction factor dependence in the laminar regime. This velocity profile, you can derive it directly by the definition of the friction factor. But yet, even though these are rigorous solutions of the Navier-Stokes equations, yet you will find that they do not agree with whatever is being theoretically predicted. Okay, this is one of the main problems of fluid mechanics. Okay, in that you may use simplifying assumptions to get the laminar flow solution, and you will also be able to get some relation for quantities like friction factor, but and that may agree with experiments up to some Reynolds number, but after that the flow undergoes a transition to turbulence from laminar flow, so the friction factor is not determined by given by this expression. Okay, so this tells you that what are the key issues in understanding turbulent flows, and how we are able to derive simple solutions in laminar flows. That's because we assume the kinematics to be simple. Right? We assume that the flow is fully developed, unidirectional, and steady. That itself simplifies all the nonlinear terms. So you are fortuitous in the sense that the nonlinear terms vanish identically due to the assumptions we made, and therefore we were able to get closed form analytical solutions. But these solutions are not always valid, as I told. Although these solutions are there, in reality, beyond a critical Reynolds number, you will find that these become invalid, or they are no longer viable, and you have to undergo a transition to see turbulent velocity profiles. Okay, so this and how do we understand turbulence in hydrodynamic stability? You don't throw out any of these terms. You keep them, and then you make an important simplification, which I'll discuss a bit later. So I'll stop here for this module. Thank you.